Okay, Chem 116, Chem 115 students. This is a slide from Chem Activity 15 that I've asked you to consider doing on your own, but it's a very useful way of thinking about doing names of ionic versus molecular compounds. It's not hard, but you're going to want to think about it in the terms of this flow chart. To begin with, you decide if the compound is ionic or molecular. If it's ionic, you have to decide if there's a metal in group 1, 2, or 13. If yes, then you don't need the Roman numerals, you don't need the prefixes. If it's an ionic compound that has not got a metal in group 1, 2, or 13, well then this is when you need the Roman numerals, and you don't use prefixes ever for ionic compounds. Molecular compounds, by contrast, are different. We won't worry about naming acids, so you don't have to do those. We're not going to learn those rules, but you do need to be able to recognize how you name molecular compounds, naming them with prefixes. I encourage you to read through those and get some practice with them. You will have examples on your homework as well. Prefixes to tell you how many of each element is present. A couple of notes about you always paying attention to realize that you want to know if something is ionic or molecular, and I'll add that to the next slide. So you'll put that in front to answer the exercises. Of course, the answers are posted on Blackboard for you, so I don't need to work them out for you. But I will comment that there's 2 acids in here that I don't care if you don't name, because we're not going to worry about sulfonic acid at all. Phosphoric acid will come up maybe, not often. Acetic acid has a lot of reasons for confusion. We will get acquainted with it gradually, but I won't force you to understand its name at this point, nor will we worry about carbonic acid for this point. So make sure you decide whether a compound is ionic or molecular as you approach these questions. All right, let's talk a little bit about the differences between ionic and molecular compounds that you can certainly read in your book, but I'll make a couple of comments, and how we represent molecular compounds, specifically thinking about Lewis structures. Lewis structures do take a little bit of time and practice, but once you catch on, they're kind of can be kind of fun. All right, so covalent bonds, we can think of the simplest possible molecule as the smallest number of atoms and electrons would be hydrogen atom, or hydrogen molecules, where you take 2 hydrogen atoms with electrons in 1s orbitals, and those orbitals are seriously going to overlap together in between the 2 atoms and be shared between the 2, so that there is one shared pair between them, providing a full configuration of 1s2 for each atom of hydrogen, and it's exactly the same as helium. There are multiple ways to represent these. All of these on the right are exactly equivalent. Some show more details than the other, but a shared electron pair is a covalent bond. Simple molecule. Molecular compound is any compound that consists of molecules with shared electron pairs, not ions, where the electrons of the valence shell are going to reach an octet by sharing. So they share enough electrons to get that noble gas configuration, the filled octet. Here are 3 examples: water, ammonia, and methane. Ammonia is a compound whose name doesn't always jump out at you, but it's one you might want to recognize. It comes up often enough. Methane is a natural gas. You'll get familiar with that with time, CH4. And each of these are covalent compounds. A good thing to notice is this diagram from the text that represents patterns that are conspicuous in how covalent bonds are typically formed by main group elements. In the Chem Activity 13 used in class, we recognize that the number of unpaired electrons tells you the number of bonds typically formed, and so the number of bonds typically formed equals the number of unpaired electrons. So that corresponds to 1 bond for group 7A elements normally, and group 6A elements will make 2 bonds, 3 bonds for group 5A, 4 bonds for group 4. Here is where group 4 elements will commonly be in compounds. They are going to make covalent compounds rather than ionic. Notice, however, that if you go beyond the second period, where you have electrons into the 3rd shell, the elements will have other possibilities for how many bonds are going to form, and these are explained by the fact that the 3rd shell has more than just an octet possible to it. The third shell includes the possibility for D subshell electrons, and so if there is an unusual configuration, you'll have to explain it by that, and we will avoid those examples in general. But that's why you get larger numbers of bonds that can be formed when you get down to the third shell of the third period. So you get funny things with phosphorus, sulfur, and chlorine, and things lower rows as well. But do remember the ones in this chart. These are very handy to remind you how bonds should be formed. Notice, of course, that the noble gases aren't going to form any bonds, except for extreme things with xenon. That's very extreme chemistry. Okay, sometimes it will take more than one bond to create an octet for each of the atoms in the compound. An example of something that works that way is going to be carbon dioxide. Carbon dioxide is shown with this red and black molecule. If you don't have double bonds, there won't be enough electrons to fill up the octet. So sometimes you're going to need multiple covalent bonds to get there. We will look at some examples that help us to see how that's done. Nitrogen, ordinary N2, which is in the air, is another example. It has to have a triple bond in order for each element, for each atom, say that carefully, to have an octet. Each nitrogen will have an octet if you realize that the 3 pairs in the middle are shared by both atoms. Same thing with carbon dioxide. Whoops, let's undo that one. But the oxygen is sharing 8 electrons there, and the other oxygen is sharing 8 electrons there, and the carbon has 8 electrons there. So they all have octets if you've got double bonds in there. So don't forget that there are different ways to represent these things. You can represent a single bond by a single line, which reflects 1 electron pair. A covalent bond is a shared pair of electrons. Shared pair of electrons. Hold that idea. A double bond can be shown by a double line. Looks like an equal sign if you're using a keyboard, meaning that you're sharing 2 electron pairs. A triple bond has 3 shared electron pairs, which is an example of nitrogen. The one with the double bond is the elemental oxygen, O2. No big deal. Something familiar. There's some compounds comparisons, or properties comparisons for ionic and molecular compounds that are shown in your textbook. Please take note of these things. They're not real profoundly crazy, but they should make some sense and things you should notice. You're either going to have ions or you're going to have molecules as your smallest components. Metals with nonmetals are the characteristic for ionic compounds, and typically molecular compounds are only nonmetals combined. And realize that that's a very small subset of the periodic table. The ionic compounds are going to be crystalline solids with very high melting points. 800 is quite hot if you think about it. And by contrast, molecular compounds will be either gases or liquids or low melting solids, so they're varied, but their melting points are much lower, and that's why they'll end up with things that are either gases or liquids. The boiling points correspond as well. They're going to be even higher than the melting points, of course, and same thing for the molecular compounds. They're in general lower. Electrical conductivity is a hallmark for ionic substances because the ions are responsible for conducting that electricity. Molecular compounds don't have that property. And water solubility is typical for ionic compounds, but not as often for the molecular compounds. It varies, though. It's not a hard and fast rule. Generally, the ionic compounds are less soluble in organic liquids, and the molecular compounds are going to be solid there. But that's a topic for another course, so don't feel like you're going to have full explanation of that for a while. Okay, so molecular formulas and Lewis structures are something we need to work on a little bit. The molecular formula shows the numbers and kinds of atoms in a molecule of a compound. We are going to use these in various ways. A structural formula is one that shows all the connections in detail among the atoms using lines to represent the covalent bonds. A Lewis structure is the one that we will use quite a bit that helps us to understand the overall shapes of molecules, and that's the goal, to show both the connections between the atoms and the location of lone pair valence electrons. These are going to be very important to understanding how the overall shape of the molecule is described. So the lone pairs of electrons are those that are not shared between electrons. They're not bonding electrons. The representations of these things can be done in a couple of different ways. So we'll see single bonds for water between oxygen and hydrogen, and then lone pairs that are shown in red above and below the oxygen. Ammonia has a lone pair and 3 bonds, and methane has only 4 bonds but no lone pairs. So the molecular formula gives the number of atoms combined in a molecule. So water is good old H2O, ammonia is NH3. That's just the molecular formula. The ionic formula always tells you the simplest ratio between ions. So that is also described as an empirical formula. You're going to explore that concept a little bit in lab at another week. So ionic formulas gives the simplest ratio of ions. The molecular formula tells you exactly which things are combined in a molecule. And the empirical formula is the only way you ever see an ionic compound represented. Now, in order to predict how Lewis structures are done, we need to have a method to help us describe these things. And the more of the examples you see, the easier it will get. To begin with, we will determine the total number of valence electrons. There's steps to follow, and try to keep these ideas in mind and use them for some examples. The total number of valence electrons are just exactly what we did in class in Chem Activity 13, where you think about the number of valence electrons, add them up. You will also need to add +1 to your valence electron tally for every time a compound has a negative charge for an ion, or you'll take away an electron if it's positively charged. We'll run into ions occasionally. Past that, then you're going to arrange your atoms in an ordinary fashion, or often it's just provided for you. You'll put 1 pair of electrons for a bond, so you start making bonds between atoms according to whatever arrangement makes sense. Typically, the element in the center of the molecule will be the one that's nearest the center of the periodic table, because it makes more bonds than the ones that are farther from the center. After that, we fill up the octets for anything except for hydrogen, because hydrogen never gets more than 2, so it'll only get a bond, and that's it. So everything that's not a central atom will get its octet filled first, if you think about how many total valence electrons are needed. After that, if the total number of electrons determined from the first step hasn't yet been used up, then at this point, you will fill an octet for the central atom, but not before. So you'll use those until the total electrons are used. Sometimes, having followed all these steps, the central atom still doesn't have an octet. Then you will need to follow the next step, and it doesn't happen every time, to rearrange electron pairs from surrounding atoms to make multiple bonds until you have an octet for each of the atoms in the formula. These rules make a lot more sense if we do examples. So let's try to draw some structures for a couple of compounds and use those rules to do it. There are 2 ways to go. With the examples we did in Chem Activity 13, you could simply go by Lewis dot structures for individual atoms and combine them and still get there quite successfully. But let's show it according to the steps that I just gave you. Alright, so nitrogen is going to be in the middle because it's closer to the center of the periodic table, and it makes more bonds than hydrogen ever will. And so we'll put the nitrogen in the middle, we'll put hydrogens around it, and follow the steps. The first thing to do is to find the number of valence electrons. For nitrogen being in group of 5, the number of electrons it provides is going to be 5. And then each of the hydrogens brings 1, so the total number of valence electrons from 3 hydrogens and from the nitrogen will be 8. And so if you think about that, you'll put in 2 electrons for each bond after you've arranged the atoms, and that uses 2, 4, 6, and so 6 electrons in bonds. You still have 2 left to account for, and surprise, they will go on nitrogen as a lone pair. So nitrogen gets 3 bonds and a lone pair to satisfy its octet. Each hydrogen has 2, and that's all it requires. Let's do another one with NCl3, which would be nitrogen trichloride. And in this case, we'll have 5 valence electrons from nitrogen. Again, how many valence electrons from chlorine? So there's going to be 3 of them. Chlorine is in group 7, so there's going to be 7 electrons for valence electrons. For a total of 21 there, plus 5 makes 26. Not tricky math, you just have to pay attention and add them up. And so we'll think about what goes in the center. Again, nitrogen is always going to be central if combined with chlorine. Nitrogen is closer to the middle of the periodic table. Follow that thought. And so arrange the chlorines around it somehow. It's not totally required to put them in any particular order. Step 2 then, after coming up with our total number of valence electrons, is to put in bonds. And the bonds are going to require a pair of dots. I'm going to use dots. You can use lines if you want to, but I'd like you to be verified that you have full octets by counting every time, so it's helpful if you can see them. So having used 6 electrons for bonds, we still have quite a few more electrons to add to the diagram. That would be 20 more to go. So in that case, we're going to put lone pair electrons on each of the chlorines in order for it to have an octet. That would require 2, 4, 6 for each chlorine. So 6 for each chlorine means a total of 3 times 6. Sounds like 18. And by the time you've used up those 18 out of what was 20 remaining, that means you should have 2 more electrons to complete the diagram. So where do the last 2 electrons go? They have to be on the nitrogen. And that way nitrogen will also have an octet, and the diagram is complete. Everything has an octet if you look closely, and all the total number of valence electrons have been used. CH4 methane is quite simple. There's nothing more to write than to think about carbon having 4 valence electrons and hydrogen bringing 1 each. And so by the time you do that, there's 4 hydrogens with 1 added electron. Doesn't seem very tricky. And that's without using the formal steps. You can still get the right answer if you realize the formula is CH4, 1 valence electron for each hydrogen, and an octet is achieved quite simply. Now, change that to put carbon with something else, and this has a name that you don't have to answer today because that's a Chem 116 topic. So let's count up the valence electrons for CHCl3. You will have a total of 4 for 1 carbon, 1 for a hydrogen, and then for 3 chlorines, again like we had up before, that would be 21, 3 times 7, and that would be, do the math, quick thinking, oh yeah, 26 electrons, same as the other example as it turns out. And so 26 electrons better show up in this diagram for it to be correct. Again, we'll have to arrange the atoms to make logical structures. And when you do that, you'll put the carbon in the middle. Carbon always likes to be in the middle. Surrounded by the other elements in the formula. No particular obligation to put them in any particular order, just that you'll realize we're looking to make octets around the carbon, so a rectangular pattern around carbon is a common way to do it. And so 3 chlorines on 3 sides and the hydrogen on the other side. Now, going from 26 electrons, step number 2 was to put in bonds. So you make bonds, and that uses up 8 electrons out of 26. And if you've been really quick with math, you can realize that that leaves us, wow, I bet it's 18 electrons. So we have 18 more to go. 18, where should we put them? So next step is to fill up the octets on peripheral atoms. Hydrogen doesn't need anything more, it's got all it needs. And so you'll put 3 sets of 6 to fill up the octets on the chlorine atoms. Okay, so having put in those, each chlorine atom now has an octet if you're looking closely. And each, the only carbon atom, has an octet. And that would be what you're looking for a correct Lewis structure. I will circle the octets, although my tool is doing it rather clumsily today. And that reflects a reasonable Lewis structure. Atoms having octets, everything except hydrogen, and a correct number of valence electrons. So 18 electrons were used up in making the lone pairs. There we go, lone pairs. Okay, let's try a couple more Lewis structures with some things that would challenge you more. I'm not going to do the silicon tetrachloride, but I want to use the H2CO example for reasons that will become more obvious, and then I'll do another one on the next slide. Let's look for the total number of valence electrons. So from total electrons, we'll include 2 for each hydrogens. There's 2 hydrogens, and so the total electrons begin with 2. And carbon is going to have, oh yeah, that's right, carbon has 4 valence electrons, and oxygen has 6. You probably saw this example already today, but let's work it through in a systematic fashion and show you how the rules can be applied. Total number of electrons is going to be 12. I like to use a tally as I run to just verify that we're following and using them all, only the ones that are described in the formula for the total valence electrons. So put carbon in the middle, that's the usual. Put oxygen on one side, put hydrogen on one side, put one other hydrogen somewhere else, and we kind of think in terms of rectangular patterns because we're looking for octets. All right, step number 2, after we come up with the total number of electrons, is to use electrons to make bonds. And so in order for each of the atoms to be connected to the others in this covalent compound, 2, 4, 6 electrons are going to be used making bonds. All right. That leaves 6 more electrons to be accounted for. The next step requires us to fill up the octets on peripheral atoms that are not hydrogen. Well, that leaves only oxygen. There's nothing else to fill here. And that's 2, 4, 6. And 6 electrons used up means we used up all the electrons that belong in the picture. Now you need to check the diagram and verify whether all of the atoms have an octet. In this case, there is not yet an octet on either carbon or the oxygen, and so we're looking for a way to fix that and verify how else we can make an octet using only the electrons allowed in this particular example. We can't add electrons, but what we can do is we can reallocate them, and so we'll rearrange how they're drawn in the diagram. We'll take 2 off the oxygen. Hydrogen's got nothing to spare. So we can take 2 off the oxygen and reassign them between carbon and oxygen as a double bond. And that means that 2 shared pairs of electrons will get carbon an octet, if you look at it closely. And it will also get oxygen an octet, realizing those ones on the side there that I crossed out are no longer on oxygen as lone pairs. Another way to represent this compound then is to use a pair of lines for the double bond. Then oxygen will still have 2 lone pairs, 1, 2. That gives it its octet. And then the hydrogens will have single bonds, and that gives carbon an octet. Not too bad, but it's one way of making sure that you have octets, and an example where you need to make sure that you use only the number of electrons allowed by the total number of valence electrons. Let's try another one. The one I'd like to try first, and this will be the last one for today, is enough for this examples, is the nitrate ion, because the ions add something different to how we do these things. So first of all, the total number of valence electrons is our step to begin with. So total number of valence, because that's what they are, electrons, begins with nitrogen, which would be 5, and then you have 3 oxygens. 3 times, what is it for oxygens? Stop and think, group 6, okay, yeah, 6 electrons. And then we have to add another electron for the negative charge. We'll haven't run into an example like that prior, so there's an example to do that. And so 3 times 6 is 18, plus 5, 23, plus 1 is 24 electrons. All right, how do we do it? Well, let's first decide which element goes in the center, because we have to arrange the atoms first, and then we'll do what we need to do with allocating electrons. Well, the element that's closest to the center of the periodic table in this formula would be nitrogen. So you put your nitrogen in the middle, put some oxygens around it, in sides that, like around there, the sides of a square, but there's only 3, so put them on as you wish. And now you make bonds. And so step 2 is to make bonds, and in doing so, we'll use up 2, 4, 6 electrons out of 24. Make that dot visible, there we go. And having done that, we have a number of electrons to go, namely 18. I hope you can do that kind of math without a calculator. 18 electrons. Well, the next step then is to fill up any non-hydrogen peripheral atoms, fill up octets. So 2, 4, 6 for that oxygen, and 2, 4, 6 for each of the other oxygens, so that's 3 of them. 3 times 6 filling up their octets would use up our 18 electrons. So no more electrons need to be added to this diagram, but is it complete? And so the third step after that, well, that was step 3, was to make the octets on the peripheral atoms. The next step, if you go back to thinking about the systematic rules, was to check for octets on the central atom if we haven't used up the electrons. Well, we used up the electrons, and yet nitrogen doesn't have an octet. So what can you do? It's like the previous example now, where you have to take some electrons and describe where they should be drawn. And so we'll take them off of one of the oxygens. It doesn't really matter because they all look kind of the same. So take 2 away from one of the oxygens and keep it between or on the same oxygen, but now put it in as a shared pair, and that gives this oxygen an octet now. The nitrogen will also have an octet, if you look at it. And I don't want to draw this too many ways because it's going to get cluttered, but I hope you realize that everything has an octet and that we use the 24 electrons, and so that explains a Lewis structure for nitrate. To be complete in this case, we actually are supposed to put a bracket around the entire formula and put the charge outside of it. As has been noted for polyatomic ions, the charge applies to the entire group of atoms, not any one atom. I hope these examples help you as you work on your homework assignments and do some practicing with Lewis structures. Good luck with those. Ask questions as you need to. See you in class.